Hello, my name is Dr. Peter Green, a Senior Lecturer at the University of Liverpool. And in this video for the Centre for Doctoral Training in Distributed Algorithms, we're going to talk about how annealing helps us sample from Bayes' theorem. So we're going to look at a classic trick that can be used to aid the performance of, for example, Markov chain Monte Carlo and sequential Monte Carlo algorithms. So in most of the videos on this channel, we are concerned with Bayesian problems. So let's say we want to infer some value x from some data y. And we write down Bayes' theorem, so you say that's proportional to the likelihood of x multiplied by the prior. And then specifically, we usually consider the situation where this is intractable. In other words, we don't have a closed form expression for the posterior distribution. When that's the case, what we do is we try to generate samples from this posterior distribution instead. So we might generate an x, let's say superscript 1 to let's say n samples from the posterior. And we do that using some clever algorithms, which for example could be Markov chain Monte Carlo, aka MCMC, or as we've described in some of the other videos in this channel, sequential Monte Carlo samplers, or SMC samplers. And of course, other samplers are available. So the geometry of the posterior distribution can make this difficult. So we're going to look at two ways in which that can happen. So the first is if the posterior distribution is multimodal. So I'm going to draw x on the horizontal axis. And then instead of writing the full posterior here, I'm going to write this pi of x. We're using our standard notation. This pi is referred to as the target distribution. So when you look at your MCMC or SMC algorithms or whatever, they'll be designed to generate samples from a target. And in this case, our target is Bayes' theorem, and it's just written as a pi, using a pi symbol conventionally. So multimodality, what if, so we're just in one dimension here, but what if our posterior distribution actually looks a little bit like this, for example. One of the things we might worry about in this situation is that our sampler only ends up generating samples from one of these modes, one of these kind of regions of probability density. So you might end up with only samples here, for example. Those samples will not be very representative of the samples from the full distribution that includes this kind of peak on the right hand side. So in terms of Markov chain Monte Carlo, that might be because your Markov chain, let's say it's wandered into this region, and the probability that it's going to jump out of this region and into here is very small. And likewise with a sequential Monte Carlo sampler, or just standard importance sampling, the same thing can happen. You might end up with all of your samples of significant weight in only this peak, or perhaps only this peak. So multimodality is something that will definitely you might be worried about. Let's say that. Okay, so we also might have the case where, let's go down here. So again, I'm going to draw the posterior on the vertical axis, x on the horizontal. It could be that our basically the probability mass is extremely concentrated. So that might happen if your data is very informative about x. It could be that the posterior kind of almost looks like this. It's almost like a spike at this particular location relative to the prior. So let's say that the prior is actually extremely wide. So again, obviously this is just a sort of graphical interpretation, but So it can be quite difficult, especially if you're in a high dimensions, to one, make sure that your sampler has located this key region of probability mass, and two, that it's tuned properly to explore this region. So all of our samplers that we've described, so say MCMC and SMC approaches, involve some kind of proposal. You have a state somewhere on this horizontal axis, and you propose probabilistically some kind of other state. It's just examples, obviously. In MCMC, if you propose to go somewhere bad, then you will probably decide not to go there through the acceptance rule, the Metropolis acceptance rule, for example. With an SMC sampler that's importance sampling based, you might end up assigning a very low importance weight to that particular sample. So one of the difficult things that you have to navigate is, you can imagine that initially when your sampler is running, you'd like it to be able to explore this whole axis very sort of thoroughly. So you'd like it to make relatively large jumps. You don't want it to just be constrained to one particular area. However, we can see that once it's actually found this concentrated region of probability density, so say your sampler ends up here, at that point you really just want to conduct a very thorough kind of local search of this area, with kind of perhaps proposing small steps to explore this region. And again, when we get here, how can we be sure that there still isn't another mode somewhere else that we've missed entirely? And now look, we've decided to just focus on this region. So these are two examples of how the geometry of the posterior can make deploying these sampling algorithms quite difficult sometimes. And a classical approach that we use to try and circumvent these issues is called, sometimes it's called annealing, and sometimes it's called tempering. So these really have their roots in material science and statistical physics, basically going back to the idea that if you heat up a metal, then it's easier for the atoms to move around, and then you cool the metal very slowly in the hope that your metal cools to its equilibrium state. It's slightly different in this case. So with the kind of analogy with statistical physics, we drop it slightly, and we'll describe why shortly. But ultimately, these methods do come under this one of these two names, and whether it's called annealing or tempering, people usually mean kind of the same thing. So don't need to worry too much about what they call it. So the key thing to note at this point is that the difficulties are coming really because of the likelihood. So if I write our target again, proportional to likelihood times prior, unless you've chosen to have a very concentrated or multimodal prior, and I can't think why you would, it means that this term is what's responsible for the geometric difficulties that we're having. So what we do with an annealing style approach is, rather than target the posterior immediately, is we're going to write subscript beta here, and we're going to write the likelihood to the power of beta. So you can see that if beta is equal to 0, then that means that our target distribution is just equal to the prior. And then if beta is equal to 1, then our target distribution is now equal to the posterior, or proportional to, I should say. So essentially, what we can do is we can run our sampler where we're gradually increasing beta from being 0, or very close to 0, to 1. And by doing that, we're gradually introducing the influence of the data on the posterior distribution, or our target distribution, I should say. And by doing that, it means we're gradually introducing those geometric features that we're finding so difficult, because, like I say, it's the likelihood that's causing those things to happen. So let's just kind of draw an example. Let's say we're going to start off with, so again, x on the horizontal. The vertical axis is just going to represent a kind of generic target distribution. Let's say we initially run our sampler with a very small value of beta. Let's say beta naught, in fact, let's say it's equal to 0. So this is just, it would just be samples from the prior. And let's just imagine that it looks a bit like this. It's quite, it's relatively large, and so it's easy to explore this space. So I'm going to write that as, well, in fact, we've kind of got a legend started here. And then I'm going to increase beta a bit. So I'm then going to set beta 1. I'm going to say that it's more than beta 0, but it's less than 1. So we're now somewhere between the prior and the sort of full posterior. And let's imagine we've got our multimodal example again. So it's the data that's causing those multiple modes to appear through the likelihood. And now we've introduced the influence of the likelihood slightly, so you might start to see just those multiple modes kind of appearing faintly, if you like. Then we're going to increase beta again, so I'm going to have a beta 2 that's larger than beta 1, but let's say, for now it's still less than 1. And again, now the likelihood is even more influential, so you might get something that looks a bit like this. So you can see that when we do this, for the low values of beta, it's generally speaking, it's easier to explore the space. As beta increases in this particular case, it's difficult to jump, let's say with Markov chain Monte Carlo, from here to here, because you have to get over this low probability region. Whereas for these low values of beta, it's relatively easy to explore this space. And ultimately what we're doing is we're introducing the kind of geometrical difficulties that we might encounter in a gradual manner. And we'll see that makes it a bit easier to cope with our sampling algorithms. Returning to our example where the posterior probability density was very concentrated, I'll draw another picture. So again, let's say that the prior is relatively wide, so we sample from that first. We can explore this space on the horizontal axis relatively easily. Beta increases a bit, and let's say it ends up looking a bit like this. You increase beta again, and it looks more like this. So the point we're trying to make is that if you, for the case where the posterior is very concentrated, if you just try to sample from that directly, it would be very easy for your sampler to just miss that area of probability density completely. Whereas if we think about targeting the prior and then gradually introducing the influence of the data, then that region of probability density concentration is introduced gradually, so it's easier for our sampler to locate. So you can imagine if our sampler is sampling from our target with beta 1, then we should end up with samples in this region. And once we've got that, then when we start thinking about targeting our with beta equals to beta 2, and we start with samples in this region, then it's relatively easy to end up with samples in this region. And so we kind of gradually home in on the region of high probability density. So what we have to do is we have to choose a sequence of beta values, and that will define our sort of separate targets. So just to be clear, what we're going to do is our sampler is going to target a sequence of target distributions. I'm going to write a beta subscript j, where we're going to start off with j is equal to 0, and then it's going to go up to a capital J. Beta 0, so that's our first target distribution, is equal to 0. And so as we saw before, that is equivalent to sampling from the prior. Beta capital J, so the final one, is going to be equal to 1. So as we saw earlier, that's equivalent to sampling from the full posterior. And everything in between, the key thing to note is that beta J plus 1 is going to be larger than beta J. So what we've got is that at each step, we're targeting a distribution where the influence of the data has increased. And this is called the annealing schedule. And as you can imagine, it's an important thing to think about when you're considering algorithm performance. If you go from 0 to 1 too quickly, then you can end up with the same issues that we've described earlier in this video. So that the probability density of your target can become concentrated or very quickly, or multiple modes can appear very quickly. However, if you do it too slowly, then that's a wasted computational resource. So your algorithm will be suboptimal. So the annealing schedule is something that needs careful consideration, and something we'll talk about later in the video. Before we do that, a final thing to think about, we won't go into it in too much detail, is that often we tune our proposal distributions so that they get smaller as we increase beta. So the idea is that, I say smaller, I should say narrower. The idea is that at these low beta values, we explore this space very thoroughly, and then as beta gets increased and the influence of the data increases, then our exploration of the space gets more concentrated. So you can imagine if you have a sample here, then when beta is equal to 0, again it's just samples from the prior, but you can imagine your proposal distribution might be relatively wide. And then let's say we end up with a sample here and we start sampling with beta equal to beta 1, then we might ask it to use a slightly narrower proposal distribution. And then likewise, we increase beta again, we might ask it to be a little bit narrower again. So this is a common trick that you might use to ensure that you start off having a very wide exploration of the space for these low values of beta, and it gets more and more concentrated as the influence of the data is increased. Exactly how you go about doing that is a little bit beyond the scope of this video, and it depends a bit on the type of proposal you're using and that kind of thing. But the principle is always the same, that you want to make sure you can explore the space very widely for low values of beta, and then your exploration becomes more concentrated at higher values of beta. Okay, so now we're going to talk about how we might adaptively choose this annealing schedule while our sampling algorithm is running. And we're going to focus on something that's importance sampling based, like for example a sequential Monte Carlo sampler. So when we start off, we've got, as we've said, beta 0, initial beta is equal to 0, and so we're therefore just sampling from the prior. So we're going to assume that you've picked a prior that's easy to sample from. So we're going to generate these samples x superscript 1 to x superscript n from the prior. Then if we're going to use an importance sampling approach, so again we've got some other videos about that on this channel, specifically under our material on sequential Monte Carlo samplers, then what we're going to do is we're going to use this as our proposal, and we're going to target the distribution pi beta 1, where we've yet to choose our beta 1, which, as we've said, is proportional to the likelihood to the power beta 1 multiplied by the prior. So the importance weights of our samples are given by the target divided by the proposal. So the weight of sample xi is going to be equal to, so target, like we said, is likelihood evaluated at sample I to the power beta 1 multiplied by the prior divided by the proposal, which is, so I should say, the prior evaluated at sample I divided by the proposal, which in this case is the prior. We generated our initial samples from the prior. And so clearly that's all just equal to the likelihood to the power of beta 1. So what we want to do next is we want to choose a kind of automatic or adaptive strategy to choose what our best beta 1 should be. Unfortunately, with importance sampling, we have a number called the effective sample size, which helps us judge how well our proposal is generating samples that are representative of the target. So what we do is, and again, there's more material on this channel, but we define this kind of normalized importance weight evaluated at xi as being our weight as described on the previous line divided by the summation of all those weights across all samples. I'll try and make that look more like an x. So that's an xi. And then we calculate something. So we use those normalized importance weights to calculate quantities of interest, the mean or variance of x. But we can also use those normalized weights to calculate what we call the effective sample size, which is equal to 1 over the summation over all of our samples of our normalized weights. The effective sample size is between 0 and 1, and like I say, it's a measure of how well our proposal distribution is generating samples that are representative of the target. And it has the property that if your proposal is equal to the target, which is obviously the ideal case, then the effective sample size is 1. And as your proposal is less representative of the target or becomes less representative, then the effective sample size drops off to 0. So what we're going to do is we're going to use the effective sample size to decide what our next value of beta 1 should be. So the key thing to note is we've already generated our samples xi, and in fact we've already got our likelihood evaluations, which often is the most computationally intensive part of these sampling algorithms. So we've done the difficult bit. We just have to pick this beta 1. So what you can do is you can try a value of beta 1. We've already got these likelihood evaluations, and so you then get your resulting importance weights relatively easily. And once you have those importance weights, then let's go down here, we can calculate our effective sample size. So what we can do is we can plot, for example, how the effective sample size changes for different values of beta 1. So in this case, you would end up with something that looks a bit like this. So on the horizontal axis, I'm going to have beta 1. And on the vertical axis, I'm going to have effective sample size. And let's say we change beta from being 0 to 1. So in this case, when beta 1 is equal to 0, then we're targeting the prior, and our proposal was equal to the prior. So that's the case where the proposal is equal to the target, and then you would get an effective sample size of 1. So kind of a data point there. Then as you increase it, that effective sample size will drop off, because as we increase it, then the target is becoming increasingly different from the proposal. So you might get a graph that looks a little bit like this. Then what we need to do is decide what kind of effective sample size we want to live with. So we set this kind of limit, which in a lot of papers is 0.5, just as an example. And we'll say, okay, we think we can live with samples where the effective sample size has dropped to 0.5. And so you can use that kind of threshold, user-defined threshold, to define what the next beta 1 should be. So for example, on this graph, if we said, okay, we're going to target effective sample size of 0.5, then you can see that that's going to say, well, this value here is what our next beta 1 should be. And so in that way, using this threshold on the effective sample size, we've been able to choose what beta 1 should be. And therefore, that's the first step in our kind of adaptive annealing schedule. Okay, so once you've done that, what happens next? Well, typically with a sequential Monte Carlo sampler, you then resample. Again, this is covered in other videos. And then you generate some new samples, or propose some new samples. But now we're going to target this new proposal. Sorry, we have a new target distribution, which is now a pi beta 2 of x, i.e. now we've got the next step in our annealing schedule. And so as a final part of this video, we're going to look at how you can adaptively choose your beta 2. So now effectively what we have is our proposal distribution. So we've now essentially got samples from pi beta 1, and we're going to target pi beta 2. So our new weights for sample xi is going to be equal to, so again we've got the target is now our likelihood evaluated at xi, but now to the power beta 2 multiplied by the prior. And the proposal is the likelihood, again still evaluated at xi, but to the power beta 1 multiplied by the prior. And clearly the prior is going to cancel here, so what you end up with is the likelihood evaluated at xi to the power of beta 2 minus beta 1. And our job, once again, is to choose a beta 2, and we want to do it such that the effective sample size drops to, we'll stick with the threshold we've picked in this example, i.e. 0.5. So very similar to the previous case, or the previous step in our annealing schedule, we've already got these likelihood evaluations. Beta 1's fixed, we decided that in the previous iteration of our sampler. What we need to do is pick a beta 2, so you can choose a beta 2, you can evaluate this term, that gives you your importance weights. Once you have the importance weights, then you can calculate the effective sample size. So again, we're going to draw a graph of effective sample size against beta 2. So beta 2 and effective sample size. And this time beta 2, well, we know it has to be greater than beta 1. So I'm going to put a kind of limit on it here. I'll say, let's say that beta 1 is here. And also, it can't be larger than 1, which we're going to write as here. Because when beta is equal to 1, then we're targeting the full posterior, if you like. And the effective sample size is equal to 1 when beta 2 is equal to beta 1, because then the proposal is equal to the target. And then we should see the graph kind of dropping off like this. So again, exactly the same procedure. We might choose, okay, let's say the effective sample size is equal to a half there. And so we read off this, then we get our new value of beta 2. And so we can continue with our adaptive annealing schedule in this way until our beta becomes greater than 1. So the key thing to note there is that if I come up with a new example graph, if the graph happened to look like this, and that this requirement for the effective sample size actually takes us beyond 1, then we just set our new beta value equal to 1, because we don't want to go beyond that. When beta is equal to 1, then we're targeting the full posterior and our algorithm can finish. So there we go. In summary, we've talked about annealing in the context of targeting Bayes' theorem with some kind of sampler, and we've described with some pictures how that can help you overcome some of the geometrical difficulties that you might encounter, specifically multiple modes or having the probability density very concentrated. We've said that it relies on you somehow picking this annealing schedule, i.e. this sequence of increasing betas from 0 to 1, and then in the context of an important sampling-based approach, specifically a sequential Monte Carlo sampler, here we've described how using a threshold effective sample size, then you can come up with this kind of adaptive annealing schedule so it can be picked automatically while the algorithm is running.